There are several things that we already know about work. For example, we know any change in energy of an object, if it's not equal to 0, is equal to the amount of work done by non-conservative forces on that object. A non-conservative force like friction could lessen the energy of an object or a system, could take away some of the kinetic or gravitational potential energy and deposit some of that energy into the ground, let's say as thermal energy. Any cases where the work was 0, we just said that the change in energy was equal to 0, and we said that the initial energy was equal to the final energy. Another way that we've thought of work is through the work equation, which says that work is equal to force times distance, and not just any force, but the force that is parallel to the displacement vector, the direction in which the object is moving, which can also be written as F times D times cosine theta, where theta represents the angle between the force and displacement vectors. And so if those two vectors point in the same direction, right, if here's some object and the force vector points to the right and the displacement vector points to the right, those two things point in the same direction, then in that case, the angle between those two vectors would be 0, and the cosine of 0 is equal to 1. And so the work done on this object due to this force F would just be equal to F times D times 1. And so we could write just F times D. If the object is moving to the right and the force is exerted maybe at some angle up and to the right, so not just parallel to the force, but at some angle up and to the right, then it becomes essential that we have the cosine theta, because we need to find the component of the force that points along the displacement of the object. And so in this case, I don't know what the angle is, but it's some angle, and the cosine of that angle is going to tell us that due to the force that is parallel to the displacement of the object that points in the same direction as that object, there's going to be some positive amount of work that is done on that object. And so you could take your calculator and plug in an angle like the cosine of 30 degrees, and you should get a positive number. And then if we keep going, we could have an object where maybe the force is pointed straight up and the displacement is still to the right. So the displacement is to the right, but the force is pointed straight up. Something like this might be like the normal force. So a box is sliding along the ground, but the normal force, which points up, is perpendicular to the displacement. And in that case, the cosine of the angle between the two vectors is the cosine of 90 degrees, which is equal to 0. And so the work done, in this case, for a force that's perpendicular to the displacement is equal to 0. And then lastly, we have things where the angle might be bigger than 90 degrees. One common example is with friction. Friction, when friction acts on an object, it always opposes the displacement of the object. So let's say the object is traveling to the right, then friction would point to the left. And those two vectors would be separated by 180 degrees, so the angle between them is 180 degrees, and the cosine of 180 is equal to -1. And if you don't know that, then really just plug it into your calculator and see that the cosine of 180 degrees is -1. And if that's -1, then the work equation tells us that F times D times -1 would be some negative number. Right? It's going to be minus F times D. So the work done by this force is going to be negative. So there are cases where the work can be positive, the work can be negative, or the work can be 0, depending on what's happening with the angle. If the angle is equal to 90 degrees, the work will be 0. If the angle is less than 90 degrees, the work will be positive. And if the angle is greater than 90 degrees, then the work will be negative. And only the force parallel to the displacement is what is doing work. Now what I'd like to do is talk about work in a different way. Let's say that we have a graph which is showing force versus position, and there's some force that's acting on an object, some constant force that causes it to move through a displacement d. The area under that curve is a rectangle. And the area of that rectangle is equal to its length times its width. The length of it is d, the width of it is f. And so f times d tells me what the area under that curve is. And f times d is equal to work. And so another way of figuring out how much work has been done on an object is to use a graph of force versus position and find the area under the curve. Work is equal to the area under the curve of a force versus distance graph. And so we've seen area under the curve type of things before. If I have a graph that maybe looks a little bit more complicated, maybe one where the force is not constant, something like this, maybe one where the force becomes negative at some point, you could take that graph and break it down into pieces that you can easily find the area of. And using those pieces, you could add up the areas of all of those different shapes and figure out what the net work done on the object is. And areas that occur above the x-axis would be a positive amount of work, and areas that are below the x-axis would be a negative amount of work. And so if there's more area below the x-axis due to a negative force than there is above the x-axis, then the net amount of work done would be negative. This is important because you might imagine all sorts of scenarios where the force that's acting on an object isn't constant. Even for something where the force is changing quite strangely, we should be able to find the area under that curve by estimating the different shapes and trying to guess at how much work was done on the object. We really can't do this. For most of the problems that we've done so far, there's these constant, non-changing forces that act on an object, and we can kind of use a free body diagram to understand what the forces are and then how much work was done on the object. But especially for cases where the forces are changing, it's useful to use a force versus position graph to find the work that was done on an object. Lastly, I'd like to just say a few things about power. We've defined power as being equal to a change in energy over a change in time. Delta E is the amount of energy that is transformed, that is converted, and delta T is the amount of time it took to convert that energy. Another way of writing this is power is equal to work divided by time. And if we know that work is equal to force times distance, then we could also write F times D divided by delta T. And here, if we recognize that D divided by delta T is distance divided by time, which is the same thing as velocity, then we can continue by writing this as force times velocity. We know that energy has units of joules, and so does work. Work also has units of joules. And power is work or energy divided by time. And power has units of work or energy, joules, divided by time, measured in seconds. And a joule per second is by definition a watt. Another unit for power is the horsepower, but the unit we will use is the joule per second, which is a watt. It is common that we find the power output of an object using a change in its energy. We should not be afraid to write things like a change in kinetic energy that occurs in a certain time interval, or a change in gravitational potential energy that occurs in a certain time interval, or an amount of work in general that's done on an object by some force that occurs in some time interval. And so the quicker that these things happen, the more quickly that I change the kinetic energy, the more quickly that the work is done on an object, the higher the power. And so there's a relationship between not just what's happening to the object, but how quickly it happens. And so we're able to express that with power in ways that we aren't able to with work or energy.